Episode 108, titled AutoML and Few-Shot Concepts, Where Automation Fits and Where It Fails, we focus on using automation wisely, because automation can accelerate good engineering, or it can accelerate mistakes.
The modern ecosystem offers tools that will search model families, tune hyperparameters, and even generate full pipelines with minimal human input.
It also offers methods that can perform useful tasks with only a handful of labeled examples by leveraging prior knowledge, which is often described as few-shot capability.
Both ideas are appealing when deadlines are tight and data is messy, but neither one replaces the need for clear goals, disciplined evaluation, and governance.
The exam-level expectation is to know what these terms mean and to recognize where they help versus where they create new risk.
Automation tends to optimize what you specify, not what you intend, and that gap is where failures happen. This episode gives you the mental guardrails to benefit from automation without surrendering responsibility for the outcome.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. AutoML is short for Automated Machine Learning, and it refers to systems that automate parts of the model development workflow, such as model selection, hyperparameter tuning, feature preprocessing, and pipeline construction. The purpose is to reduce manual trial and error by letting an automated search explore combinations of algorithms and settings under a defined evaluation procedure. AutoML systems often include choices about preprocessing steps, feature encodings, missing value handling, and candidate models, then evaluate them using cross-validation or holdout splits to select a best-performing pipeline. Conceptually, AutoML is an optimization engine wrapped around a modeling pipeline space. It can produce strong results quickly because it systematically explores options that a human might not have time to test. However, its quality depends on the quality of the search space and on the integrity of the evaluation procedure it uses. At exam level, the key definition is that AutoML automates selection and tuning, not that it magically understands your business problem. AutoML is often most valuable for creating strong baselines quickly under time pressure because it can provide a credible starting point before you invest in deeper feature engineering or specialized modeling. A strong baseline is a reference point that tells you whether the problem is learnable with the available data and how much performance is possible with standard techniques. Under pressure, a baseline also helps you decide whether you need to change the dataset, collect more labels, or revise the target definition before you sink time into manual tuning. AutoML can also help teams avoid the trap of prematurely committing to a familiar model family because it tests a broader set of candidates systematically. In professional workflows, it can be a way to accelerate iteration while you focus on data quality and evaluation design, which often matter more than the specific algorithm. The key is to treat AutoML as a baseline generator and search assistant rather than as a final authority. When you use it this way, it becomes a time saver without becoming a governance risk.
AutoML cannot replace clear goals, clean data, and governance because it does not define the objective for you, and it cannot fix conceptual problems in labeling or decision design.
If the metric is wrong, AutoML will optimize the wrong behavior efficiently. If the labels are leaky or poorly defined, AutoML will produce impressive numbers that fail in production, and it may do so faster than a human would.
If the data pipeline has shift issues, missingness artifacts, or inconsistent time boundaries, AutoML can bake those flaws into a pipeline that looks strong under flawed evaluation.
Governance also requires interpretability, documentation, and reproducibility, and AutoML may produce pipelines that are difficult to explain unless you impose constraints. This is why a mature team uses AutoML after defining the decision problem and evaluation plan, not before.
Automation can explore, but it cannot decide what is ethically, operationally, or legally acceptable.
The exam often probes this by asking what AutoML misses, and the correct answer is judgment and context.
Few-shot learning refers to the ability to learn a task from a small number of labeled examples by leveraging prior knowledge encoded in a pre-trained model or representation. The idea is that if a model has already learned general patterns from large-scale data, it can adapt to a new task with only a few examples because it is not starting from zero. Few-shot approaches are common in modern language and vision systems where pre-trained representations are strong enough to generalize with minimal supervision. In practice, few-shot often involves providing a handful of labeled examples to guide the model's behavior, shaping how it applies its prior knowledge to the new context. The advantage is that you can stand up useful capabilities quickly when labeling is expensive or slow. The risk is that few examples may not represent edge cases, leading to brittle behavior that looks good on a small sample, but fails under broader usage. At exam level, few-shot means learning with few labeled examples due to prior knowledge, rather than due to a clever new learning algorithm alone.
Zero-shot refers to performing a task without any labeled examples for that specific task, again relying on prior knowledge and the ability to generalize from instructions, descriptions, or related concepts. In zero-shot settings, the model uses what it already knows about language, categories, or patterns to infer how to perform the task, often based on natural language prompts or label descriptions. This can be useful when you need a quick capability, when labels do not exist yet, or when tasks are too numerous to label individually. The limitation is that zero-shot performance can be unpredictable, especially in niche domains where the model's prior knowledge may be weak or biased. It also raises governance concerns because behavior can shift with subtle changes in phrasing, making the system difficult to standardize. Zero-shot can be a powerful prototyping tool, but it is not a substitute for proper evaluation when decisions carry risk. At exam level, remembering that zero-shot means no task-specific labeled examples is the key definition. Identifying scenarios where few-shot is reasonable and safe requires thinking about decision impact, variability, and the cost of being wrong. Few-shot can be reasonable when the task is low stakes, when outputs are used to assist humans rather than to automate irreversible actions, and when you can monitor and correct errors quickly. It can also be reasonable when the label space is simple and the domain is close to what the pre-trained model likely understands, such as generic sentiment or broad topic classification. In cybersecurity, few-shot can be safer for triage assistance, clustering, summarization, or first-pass categorization where a human remains in the loop rather than for automated blocking decisions. Safety also depends on whether the few examples cover important subgroups and edge cases, because sparse examples can hide failure on minority patterns. The disciplined approach is to treat few-shot as a way to bootstrap, then expand evaluation and labeling as soon as possible. Few-shot is therefore reasonable when you can bound risk and validate quickly, not when you need guaranteed correctness across all cases. A major risk with both AutoML and few-shot methods is trusting automated results without validation and leakage checks, because automation can produce strong numbers for the wrong reasons. AutoML may inadvertently exploit leakage through preprocessing, time leakage, or entity leakage if the evaluation split is not designed correctly. Few-shot systems may appear correct on the provided examples while failing broadly, and they can produce confident outputs that hide uncertainty. The prevention pattern is to use strict evaluation boundaries, preserve a holdout test set, and ensure preprocessing and feature selection occur within training folds only. You also validate on realistic slices, such as time-based splits when the future differs from the past, because automation is especially vulnerable to optimistic evaluation. When results look too good, treat that as an audit trigger, not as a conclusion. The exam expects you to be skeptical of automated success until it survives disciplined validation. Interpretability and compliance are recurring themes because automation can hide assumptions by producing pipelines that are hard to explain and hard to audit. An AutoML system might choose complex ensembles, unusual transformations, or feature selection steps that improve a metric but undermine interpretability. Few-shot and zero-shot systems can be even harder to explain because their internal reasoning is not transparent and their outputs can change with context. In regulated environments, you may need to constrain AutoML search spaces to interpretable models, or require explanation artifacts that meet governance standards. You may also need to document how few-shot examples were chosen and how outputs are controlled, because ad hoc prompting is not a stable policy. The professional posture is that compliance requirements define what kinds of automation are acceptable, not the other way around. If the system cannot be explained and audited sufficiently, it may not be deployable, regardless of performance. Automation does not remove compliance obligations, it often increases them. Cost trade-offs matter because AutoML often saves human time while increasing compute usage, since automated search can run many training trials across many configurations. This is usually acceptable when compute is available and deadlines are tight, but it can become expensive if the search space is large or if models are heavy. In some cases, an AutoML run that looks convenient can consume far more compute than a well-guided manual approach, especially if it explores complex ensembles extensively. Few-shot and zero-shot approaches may reduce labeling cost, but they can increase the cost of monitoring and human review if outputs are inconsistent or require frequent correction. This is why the right cost comparison includes human time, compute, and operational overhead, not just one dimension. In practice, automation is most valuable when it shifts effort from repetitive tuning to higher value work like data quality and governance. The exam-level message is that automation changes cost structure rather than eliminating cost. Documentation is non-negotiable because automation outputs must be reproducible and auditable, especially when they influence important decisions. For AutoML, you need to document what pipeline was chosen, what hyperparameters were selected, what preprocessing steps were included, and what evaluation procedure produced the selection. For few-shot and zero-shot systems, documentation includes the example set, the prompt or instruction pattern used, and any constraints or safety rules that shape outputs. Without documentation, you cannot reproduce results, investigate failures, or demonstrate compliance, and you cannot distinguish drift from configuration changes. Documentation also supports continuity when team members change, because automated systems can produce fragile setups that only one person understands. Treating automation outputs as first-class model artifacts is part of responsible practice. The exam expects you to emphasize documentation because it is a core governance control. Communicating automation as an assistant, not authority, is important because it sets expectations and preserves accountability. AutoML can propose a strong pipeline, but humans must confirm that the metric aligns with the decision goal, that leakage boundaries are respected, and that operational constraints are met. Few-shot and zero-shot systems can provide useful outputs quickly, but humans must verify that those outputs are reliable enough for the intended use and that edge cases and bias risks are understood. This framing also helps stakeholders accept that automation does not remove responsibility for outcomes because the organization still owns the decisions made with model outputs. When automation is framed as authority, people are tempted to accept results without scrutiny, which is exactly how leakage and misalignment slip through. When it is framed as an assistant, scrutiny becomes part of the workflow. This is not pessimism, it is governance realism. The anchor memory for episode 108 is that you automate search, not judgment, and validation remains yours. AutoML can explore model spaces and tune settings, but it cannot define what success means in your domain or whether a pipeline is ethically and operationally acceptable. Few-shot and zero-shot methods can leverage prior knowledge, but they still require evaluation to confirm reliability and to identify failure modes. Validation remains yours because you must enforce clean splits, prevent leakage, confirm calibration, and test performance under realistic conditions. This anchor also reminds you that governance is human work, even when model training is automated. When you keep this anchor in mind, automation becomes a productivity booster rather than a risk amplifier. It keeps you in control of the decision process. To conclude episode 108, titled AutoML and Few-Shot Concepts, Where Automation Fits and Where It Fails, choose an AutoML use case and then state your validation step clearly. A strong use case is building a baseline classifier for an imbalanced alert triage dataset under time pressure where you need a quick sense of achievable performance and which model families are promising. AutoML can generate candidate pipelines and provide a strong baseline, but your validation step is to enforce strict splitting that matches the deployment timeline. Fit preprocessing inside each fold to prevent leakage, and reserve an untouched final test set for a one-time confirmation after tuning is complete. You would also review the chosen pipeline for interpretability and compliance fit, documenting the full configuration so results are reproducible. This validation step matters because it converts automation from a black box suggestion into a controlled, auditable decision. When you can state the use case and the validation step together, you show the exam-level competence, using automation to accelerate search while keeping judgment and evaluation discipline firmly in human hands. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.